In this chapter, we're going to be introducing logic and proofs. In this lesson, we're going to look at identity proofs.
Okay, so everybody, in this lesson, we are going to take a look at what we're going to call here identity proofs. Okay, identity proofs. So in like a previous lesson here, video here, we took a look at the rules that allow you to transform expressions from one form to another. Okay, and we looked at those. Those were our what we were calling our equivalence proofs, and we used the equivalence proof as just a way of looking at what a tabular proof might look like. And we were really explicit about our thinking with questions that we were already very comfortable with. You know how to solve those kind of equations. We're just being very, very clear about why we can do the steps that we do here. So, and we were taking advantage of, in that particular case, they were taking a huge advantage of equivalence. Okay, the equivalence part of the equal signs and what we can do, moving back and forth with those equal signs there. Now what we're going to do is we're going to do a slight variation of that. Okay, in an identity proof, we work independently on both sides of the expression to demonstrate that the two sides are equal. So essentially what we're going to do here is we've got a statement of equality, but we don't know that the equality is true. We don't actually know that the left side and the right side are the same. That's what we're trying to prove here. In an equivalence proof, we're assuming it, okay? And then we're taking advantage of it. We've got rules that allow us to move ahead, assuming that equality is true. Well, here we don't. So you are not allowed, like it says right here, you are not allowed to move any term from one side to the other, because that is only allowed if you can demonstrate that, or sorry, if it's true that the both sides are equal. So the word equation is often loosely used to refer to an algebraic expression for which there are a finite number of values for the variable x that's satisfied, or possibly an infinite number, okay, but not all the real numbers. An identity, by contrast, like it says right here, is a statement that is true for all. Whoops, sorry, I was expecting that to be a highlighter. So let me go through and erase that, and then we'll go back to this. For true for all values of x, okay? All of them, across all of the real numbers there. So sometimes you're going to see that symbol with the lines there when referring to identities, okay? Just something that we'll use there. So proofs are also frequently used when establishing that an algebraic expression is in fact an identity, okay? So we're going to work through some examples of this. What we're not going to do at this point here is show our justification from one step to the other like we did with the equivalence proofs. We're going to kind of assume that those rules are now very, very comfortable, okay? And so what we're going to do with our identity proofs is we're going to work on one side or the other, or even both, but we're going to work on them separately, and we're going to use those rules that we looked at with the equivalence proofs to take each side here and rewrite them in a form that makes them equal to one another, or at least to verify whether they are in fact equal or not. Anyway, let's have a look at some examples that are kind of done for us, and then we'll do a couple of examples together. Okay, so we're supposed to show that 1/4 plus 1/12 is equal to 1/3. Now we're going to assume at this moment in time that we're not 100% sure that that's true, that they're equal. Now, this isn't, maybe strictly speaking, an identity proof because there's no variable here, okay? But this is going to at least give us that starting point, give an idea of what this is supposed to look like here. So we've got the left side and the right side, okay? We're going to work on them independently like you're seeing here. There's not much we can do on the right-hand side. That's it. It's 1/3. But on the left-hand side, there is some stuff that we can do here, right? We've got two fractions, so on the right-hand side, it's just one fraction, so it's maybe a good idea to add those two together. Well, I know that we need common denominators to do that, and between 4 and 12, the lowest common multiple of those two numbers is going to be 12. So I know that I got to multiply that 4 by 3, which means to keep that fraction there still equal to 1/4, I got to multiply the numerator by 3. So that gets me 3/12 plus 1/12. Then I know, and I think back to my equivalence proofs here with the division property there, that I can take that 3 12ths plus 1/12, and I can write that as 3 plus 1 over 12. It's like almost like me factoring out that 1/12. And then I can add that 3 plus 1 to get my 4. And then basically what we're saying here is this is like 4 over 4 times 3. And then 4 divided by 4 is 1. And there we go. I've got it down where the left-hand side is now equal to the right-hand side. I've shown that that's a true statement here. And again, what we're encouraging people to do is when you get it down to this point here, left side equals right side, we want to write it like that. That's what we're going to use to kind of end this kind of a proof here. That tells me that I believe I'm done. I've accomplished what I need to do here. Let's take a look at another one. Okay, now this next example here, and again, not really great for like illustrating identities, but we're kind of working towards that here. There's no variable here, but I want to show that 8 minus 3 squared plus 5 is going to be equal to 8 squared minus 6 times 8 plus 14. Okay, so again, I split it up, left side versus right side, just like I've got written there. And now what we're going to do is we're going to look at both sides independently. So on the left-hand side, and when I say that, I mean we're going to follow the order of operations. So within the brackets there, I've got this 8 minus 3, and I know that that's going to be equivalent to 5. Then I apply the square, so 5 squared is going to give me 25, and then I apply the addition, and I get 30. So the left-hand side is equal to 30. On the right-hand side, I've got these two terms here. I've got 8 squared, and then I've got this 6 times 8. There are two different terms here. Normally, I would do the power first here, but they're in two different terms, so it doesn't really matter. So 8 squared is 64, and then 6 times 8 is 48. And now I'm just going to apply the subtraction and the addition kind of in order, moving left to right. So 64 minus 48 is going to be 16. And then I add 14 to that, and I get 30. And there we go. Left side is equal to right side. So we conclude, like it says right here, that the original expression is true. Okay, so now we're going to look at something that we would really consider an identity here. So we're going to show that 1 over m plus 1 plus 1 over m squared plus m is equivalent to 1 over m. So on the right-hand side, there's really not much for me to do. I'm just going to leave it like that, 1 over m. Okay. Now, that's just a single fraction. So on the right-hand side, I've got two fractions. And I want to add them together here. But the first thing I'm going to do here is factor, because remember, for me to come up with to add them together, I need a common denominator. But I want to be clever about that. I don't want to just multiply the two denominators together, because that might create an expression that's unnecessarily complicated or large. So I want to do this as smoothly as I can here. So first of all, I'm going to factor that denominator, that m squared plus m, and I get 1 over m multiplied by m plus 1. So now I can see that I've got a common factor of m plus 1 between those two. So for me to add these two fractions together, what I need is an extra factor of m in that first term, and specifically in the denominator. So I put 1 there, but that requires that I got to put 1 in the numerator. And so now I get m over m times m plus 1 plus 1 over m times m plus 1. The denominators are the same, so I can add the numerators together, and I get m plus 1 over m times m plus 1. And then notice what happens. Okay, I've got some canceling occurring. Okay. Now, what I should really do here is I should include in this particular case here that m cannot equal -1. Can I get to this fact that m cannot equal -1? But notice that I still get it down to this 1 over m. M plus 1 divided by m plus 1 is going to be equal to 1 for all values. Okay, except for -1, it's going to be equal to 1 for all values. And so I get 1 multiplied by 1 over m. And so there we have it. The left side is equal to the right side. Okay, let's keep going. Now for this next one, we're told to show that x minus 3 squared plus 5 is going to be equivalent to x squared minus 6x plus 14. Okay, so when I look at the two sides there, I'm going to look at them separately here. That right-hand side, x squared minus 6x plus 14, I'm going to leave it like that. What I'm going to do here is I think it might be easier just to do the work that's being applied on the left, like that square. So I'm going to apply that square. And you got to be careful about that. It is very tempting. Oh my gosh, is it ever tempting for people to make this into x squared plus negative 3 squared and just make this x squared plus 9. Forgetting that there is more to binomial multiplication than that, right? This is not true. So it's better to write those two factors, those two identical factors side by side, so that when I multiply that out here and I distribute, okay, because I'm going to have to apply distribution here, x times x, then x times negative 3 times x, negative 3 times negative 3, and that becomes x squared minus 6x plus 9, and then with that plus 5 on the outside there. Now, I really like that because I can see this x squared minus 6x on both sides. That's wonderful. And then 9 plus 5 is 14. And so there we go, x squared minus 6x plus 14. The left-hand side is equal to the right-hand side. So there we go, that's an identity. Now this next one probably isn't even really necessary given what we just did here. But again, just to hit that idea, just to make sure that this is abundantly clear, that x plus 3 squared is in fact equivalent to x squared plus 6x plus 9. Okay, that's going to be just the sole goal here. The right-hand side is good. Okay, I'm going to expand the left-hand side to get to the right-hand side. So x plus 3 squared is x plus 3 multiplied by x plus 3. And if you really need to think of it, so what we're doing here is we're splitting this up here. And if it looks like if it kind of feels like I'm like making a bigger deal out of this than necessary, it's only because I've watched even really, really strong students get this particular little bit of algebra wrong, right? This x plus 3, the x gets multiplied by x plus 3, and then the 3 gets multiplied by that x plus 3. That x plus 3 gets distributed to both terms, and then you distribute the x to both terms, and then we group together the like terms to get that x squared, so they get that x plus 3 squared is equal to x squared plus 6x plus 9. And again, the left side equals the right side, so I know that that is an identity. Okay, so now this one is kind of going to leave us with a little bit of freedom to do what we want with this one. There's a little bit of structure here, and actually I'm a little embarrassed by this. The structure is set up that really it should have looked more like this. I got those on the wrong side there, and I apologize for that. It should look more like this. So that when I set this thing up here, I've got the left side is x minus y multiplied by x squared plus xy plus y squared. And I'm going to show that that is equal to x cubed minus y cubed. Now, on the left-hand side, and this is the one that probably requires the most work because I can do some expansion here. It makes sense. What I'm going to do is I'm going to take these two terms here and I'm going to distribute them to that trinomial. So it's going to be x multiplied by x squared plus xy plus y squared minus, and then we're going to take that y and multiply it by x squared plus xy minus y squared. Okay, now we're going to distribute the x through the trinomial. Okay, and so that's where we're going to get the x cubed plus x squared y plus xy squared. And now we're going to take really the negative y and we're going to distribute to the three terms in that trinomial there. So negative y multiplied by x squared will be negative x squared y. Then we're going to get negative xy squared and then negative, oops, sorry, and that should have been, oh, I'm sorry, this is a positive here. Sorry, that didn't come through. And so that'll be negative y cubed at the end here. Now, when I group together like terms, notice I get this x cubed, the x squared y and the negative x squared y cancel. The xy squared and the negative xy squared cancel. And so what I'm left with x squared minus y squared. And so what I've got here is that the left side is equal to the right side. And so I know that that's an identity. Okay, and now finally this one. We're going to prove that x to the m, x to the n is equivalent to x to the m plus n. Okay, so And again, we're not given any kind of lead into this, so we're just going to kind of do it ourselves here. And this is a relatively obvious one. I think a lot of you, when you sit kind of back and think about it, it makes sense. You understand why this is true. We're just going to add a little bit of structure to this. So first of all, we're going to write down here x to the m, x to the n. There's our left-hand side. And then we've got x to the m plus n on the right. And what I'm going to do is I'm going to take a look at that left-hand side here, and I'm going to break up that x to the m first. Then I'm going to break up that x to the n. Now, what that means is I'm going to have a bunch of factors of x. So I've got one factor multiplied by another factor, the second factor, then the third factor multiplied by dot, 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 and we're going to go all the way up to the mth, the mth factor. Over here, then, I'm going to break up that x to the n, and I'm going to have my first factor, and then my second factor, and then my third factor, and multiply by, and I'm going to go all the way up to the nth factor. Now, the little subscripts there, these are just ways of labeling. This is just so that I can see, okay. I have got 1, 2, 3, 4, all the way up to the m number of factors, and I've got 1, 2, 3, all the way up to the n factors here. But when I remember multiplication, I can associate with multiplication. I don't have to. So I can drop those parentheses, and this simply becomes x1 times x2 times x3. And then what happens here is I get dot, dot, dot. I get up to the x to the m. And then I've got another one here. So basically, this one here becomes the next term here. So I'm going to add one more to that. So that next one is going to be my x plus 1th factor. That next one becomes my xm plus 2th factor. Okay, so I ended up at x to the m, and then I added another one, and then I added another one, dot, 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 until I get up to the x sub m plus nth factor there. And so putting that all together, remember that the exponent tells you how many factors you have. Well, I've just demonstrated that I have m plus n factors, and so this is going to be equal to, and I probably should have put equal signs all the way down here, this is going to equal x to the m plus n, in which case the left side is equal to the right side. Okay, now there's an awful lot more that could be said about these sorts of proofs here. And I suspect that it's likely the case that you may have seen some of this sort of stuff done in a trigonometry chapter, a trigonometry course, when you're working with what we call trig identities. Very, very similar sort of thing going on here. Again, this is just kind of an introduction just to give you a sense of how everything works here. And I hope that, I hope that gives you, like I said, just a little bit of a sense of how these sorts of things work.